Year 11, here are your 5 a day. Here are the answers. So, today we are starting on a new chapter called Kinematics. And our first lesson is on position, velocity and acceleration. We're going to have a look at the relationship between them and how we can find values for them. So displacement is often represented by the letter S. Sometimes it is represented by the letter X, and it means the position of the thing that we're talking about with respect to a point. Now, we can differentiate a function of S to give the velocity, because velocity tells us the rate of change of displacement with respect to time. So velocity is ds by dt. Then we can differentiate velocity to give acceleration, because acceleration is the rate of change of velocity with respect to time. Our position, we tend to talk about particles, so we don't have to worry about other external factors like air resistance, and it tends to be relative to a fixed point, which we called O, or the origin, on a line. We're just going to look at movement in straight lines, and the position can be to the right or to the left of O. By convention, we say that to the right of O is positive. So here is our starting point. Sometimes we start to the right or to the left, but this way is positive, this way is negative, just like on a number line. Now we need a few definitions. So average velocity is the change in position divided by the change in time. Instantaneous velocity, or what we just normally call velocity, is the rate of change of position with respect to time. Speed is the magnitude of velocity. So your speed is always going to be a positive value, whereas velocity can be positive or negative because it tells you what direction you're moving in. Average speed is found by calculating the distance travelled and dividing it by the change in time. Average acceleration is the change in velocity divided by the change in time. Instantaneous acceleration, normally just called acceleration, is the rate of change of velocity with respect to time. These ideas you should have covered in methods already. These 3, 1, 2, 3 formulae, you should pause the video and write down now. So let's have a look at how we use these ideas. I will give you a moment to read this question. Okay, so it's important that you're aware of the units of measurement being used here. We've got centimetres and we've got seconds. Velocity is the derivative of the displacement. It's a good idea with these kinds of questions. Start by stating the information that you're given. So here is my displacement function. My velocity is the derivative of this, so I write what that's equal to. This is measured in centimetres per second. Initial velocity means when t equals 0, at the beginning of when the time is being measured. So when t is 0, I substitute t equals 0 into my velocity function, and that gives me v equals -7. I need to interpret that in terms of the situation. So the particle is moving at 7 centimetres per second to the left. The negative tells me it's moving to the left. To find when the velocity equals 0, that means that the dx by dt, or just v, is equal to 0. So I can use this expression that I found, I set it equal to 0, and I solve for t. What I should have done is included my units. So I should have written t equals 3.5 seconds. That's the when part. I also need to say where. Where means I take my time and I substitute it into my expression for the displacement. I can do that on my calculator. That gives me negative 6.25, so I need to interpret it within the context of the question. That means 6.25 centimetres to the left, because it's negative, of O. So same situation, 2 more questions. Average velocity for the first 4 seconds. Remember that average velocity means change in position divided by change in time. So I need to work out my position when t is 0, my position when t is 4, and they get substituted in for x2 and x1. When t equals 0, x equals 6, that's quite straightforward to see. When t equals 4, again you can use your calculator, x equals negative 6. T2 is 4 seconds, T1 is 0 seconds. Substitute those values into my formula and I get negative 3 centimetres per second. Average speed for the first 4 seconds then. Remember that average speed equals distance travelled divided by the change in time. So we have to work out how far the particle travels between 0 and 4 seconds. Remember from part B, we found that the particle stops at t equals 3.5. So if I draw a line where this is 0, before we saw that at t equals 0, my particle starts at 6 centimetres to the right of O. I need to work out what happens to it, or where it is, when t equals 3.5. I substitute 3.5 into my expression for the displacement. That gives me x equals negative 6.25. So when t equals 3.5, we're at negative 6.25. And then I worked out in part C, when t equals 4, my scale isn't great here, but when t equals 4 seconds, I'm at negative 6. So my particle starts here, travels in this direction, and then turns around and goes back to here. So I need to work out this distance and add it to this distance. And that gives me 12.25 in the first 3.5 seconds. Oh, sorry. So this part here, so from 6 to negative 6.25, that's 12.25 in the first 3.5 seconds. In the next 0.5 seconds, it moves 0.25 centimetres back in the other direction. So in total, the distance travelled is 12.5 centimetres divided by the change in time, which is 4 seconds. And so my average speed is 3.125 centimetres per second. And see, these values are not the same. Average speed does not equal average velocity. Sometimes it will, mostly if you have a situation like this where we're turning around, it will not be equal. So here's a second example. I'll give you a moment to read it. So our velocity is the derivative of the displacement. So I just differentiate this expression here. My velocity equals 6t plus 2. I'm not given my units of measurement here, so that would be units per second. Acceleration is the derivative of the velocity. So that's just 6, and that would be units per second squared. See, I've written these in function notation because that means that I can show these parts really easily. So calculating the velocity at 1, 2 and 3 seconds, I can say v of 1 equals, substitute 1 in. Oh, I've decided it's meters apparently. It doesn't say it's meters anywhere, but let's say put that there. Now we can state the units properly. Then v of 2 and v of 3. Acceleration, I can do the same thing. It remains constant because there's no t. To describe the motion, I can say the acceleration remains constant for the first 3 seconds. And in fact, I can see that it will always remain constant because there's no t involved. The velocity increases by 6 meters per second for the first 3 seconds. The particle will continue to get further away from the starting point to the right-hand side as time increases. So that's all of the examples that you need in order to answer questions 1 to 6 from 22A now. Make sure for questions 1 and 2 you interpret your answers and use the words left and right of O, or travelling to the left and to the right when you're talking about velocity, rather than just writing positive or negative. There's your answers for 1 and 2. Here's questions 3 to 6. And there's your answers for that. Let me know if you have any questions. Thank you.